Okay, no more relativity. Moving on to quantum physics. Packer says this is about the ugliest picture of something he's ever seen.
Seen your baby pictures?
It's a dead fly. That's why his eyes are all sunken in.
They're not that ugly.
And he's missing a bit of its antenna here. This image was taken with a electron microscope. It's not a visible image. It's not something that you could not see these things with visible light, these details. And the reason that you cannot see these details with visible light is that visible light waves are much bigger than these details. So you can't measure something that is smaller than your measuring device. When it comes to waves, your measuring device is your wavelength. And many of the details in this picture are smaller than that. Particularly these very tiny hairs and other things in here that are very, very tiny. Your wavelengths are, half a micron. Remember that visible light is in the 400 to 700 nanometer wavelength range. And 400 to 700 nanometers, remember that an atom is about a half of an angstrom. So 2 atoms make up 1 nanometer. And so you're talking 500 to 1,000 atoms for every wavelength of light. And hundreds of atoms across is the smallest thing that you could possibly get any kind of resolution with, and that kind of resolution would be pixel resolution, which is not what you're looking for. When you want to resolve something, you want to have hundreds of pixels resolution. And so really a microscope, a visible light microscope, can only get you down to the micron range, which is why they call them a microscope, because they can get you to the micron or 1/1,000,000th of a meter kind of range. But many things are smaller than that we want to study, so we use electrons. Well, how's an electron going to give you something smaller? I mean, electron is a particle. How is it going to give you any kind of image? And that is the question, one of many questions that is answered with quantum theory and quantum physics. Here they show a nice little representation, which really has very little to do with what actually would be an atom. Here they show what a representation of an atom might look like in a two-dimensional structure, in a two-dimensional cross-section, where you have this nucleus at the center, and then these what we call atomic clouds or electron clouds or valence clouds, however you want to talk about them, electron shells, another way to talk about them. These represent domains of electrons, I suppose you could say. And this, of course, is nothing like an actual atom. We have no idea what an actual atom would look like because atoms are way smaller than the light that we see with. So once again, we run into this problem that our measuring device is much bigger than the thing we're trying to measure. Even more so, the scale of this is way off. Does anybody have any idea what the scale of an atom is compared to the scale of the nucleus?
Hundreds of thousands.
Well, maybe not quite that big, probably more like thousands. So if the atom was a baseball stadium, then the nucleus would be the pitcher's mound or smaller. Okay? So it's quite a bit smaller. Um, it's just a big difference in size, even though almost all of the mass is inside the nucleus. 99.9%, of the mass of an atom is inside the nucleus, and all that mass is concentrated in a volume that is 1,000th the size of the entire atom, or maybe smaller. So it's very, very small in size, and that's something we do know. We don't know because we looked at it. We know because of a particular experiment done by one of my favorite scientists.
Richard Feynman.
Not Richard Feynman. Well before Richard Feynman. They actually, let's see, where do they... Let's look for this experiment. I'm sure it's here somewhere. It's probably in the atomic section, which is a couple of chapters down the road here. It's actually back in chapter 8 and in chapter 30, actually. So this is one of the first experiments that was ever done with atoms, with actual atoms. Because we can't see atoms, it takes a different kind of science to kind of detect them and understand something about them. And Ernst Rutherford was one of the first people to figure this out. Ernst Rutherford was the first Baron Rutherford of Nelson, New Zealand-born British physicist, and he discovered the nucleus of the atom. He was the first one to figure out what the atom kind of looked like, quote unquote, or what its composition was. And his experiment was really quite ingenious. Because you can't see an individual atom, he decided to use a measuring device that was about the same size of an atom. And this is what his experiment looked like. Let's see if we can view this in a little bit larger format. There we go. So he had a lead box with a radioactive source in it, something, I think he had radium in it or something like this. And radium gives off a radioactive particle called an alpha particle, which is actually a helium particle. It's a helium nucleus. The helium nucleus, he didn't know at the time that it was a helium nucleus. He just knew that it was a positively charged, massive particle that would come out at high energy, high speed, when you had radium. But the helium nucleus turns out to be the smallest nucleus in the entire periodic table. It's even smaller, technically. Well, I guess technically it's not smaller than the hydrogen nucleus, but it's smaller than the hydrogen atom. So it was the smallest particle that had a pretty good mass to it that was really known at the time. Electrons are quite a bit smaller, but they have almost no mass to them. So anyway, these particles are both easy to detect in many ways. Because they have a large mass, they're easy to detect. Because they have relatively large mass. Because they have a big charge, they're easy to detect. And because they have a lot of energy when they're coming out of radium, they're pretty easy to detect. So these alpha particles, as they were called, were being used for a lot of things. And the thing that Rutherford wanted to use them for was to determine what the structure of atoms was. At the time, it was thought that atoms were just kind of like this continuous substance, kind of like cake. And that there was charges inside of this cake that were kind of like raisins in the cake. And he was trying to test this theory. And so he took a piece of gold and he hammered it out to extremely, extremely thin layer, gold foil essentially. You can hammer out gold till it's only a few atoms thick. And so what he was trying to do is he was trying to make a material that was only a few atoms thick, which is difficult to do with most materials, but gold you can do it with. And then he would fire these alpha particles at the gold and see what happened. And his thought was that most of them would go straight through, just like firing bullets through a cake. But every once in a while, one of these bullets would encounter one of these charges, one of these raisins in the cake, and would get close to it, and that would make it turn because it would get attracted or repelled by those charges that are in the cake. And that's what he thought would happen. And that's exactly what happened. You have these bullets going through, these alpha particles flying through the gold foil, and most of them went straight through, and some of them deflected off slightly, and they had this detector around here. The interesting thing was that he had a student working for him who had a thought. He said, I wonder if any of these particles are coming back, if any of them are bouncing back. And so he extended the detector all the way around to the backside, and what they noticed is that about 1 in 1,000 particles bounced almost straight back. This contradicted the theory that atoms are made of something like cake with raisins in it, and that we were shooting bullets through it. Because if you shoot bullets through cake, no matter what kind of raisins you have in it, the bullets are not going to bounce back. And so from this theory, they discovered that atoms must have some really concentrated, supermassive objects in them that are positively charged. Because they have to be positively charged or they wouldn't bounce back a positive particle. And they have to be supermassive or they wouldn't be able to bounce back a massive particle. And so they discovered the nucleus of the atom at this time. And they said, atoms are not like cake with raisins in them. Atoms are kind of like solar systems with a massive thing in the center, all the mass kind of concentrated in this tiny little spot, and pretty much empty space everywhere else. And the planets in these little atomic solar systems are the electrons. The nucleus in these little atomic solar systems are like the sun, you know. And that was the new model, or the Rutherford model of the atom. But what was so interesting about this experiment? Why is this experiment different than other experiments? When Newton was doing experiments, he was rolling balls down ramps and dropping things and studying the data from people who had been studying the stars and the planets moving around in space. And he figured out how gravity worked from all these experiments, from observing what gravity does. Why is this any different? Why is this so special? Exactly. This is not a direct experiment. This is an indirect experiment, an indirect measurement. I kind of like saying this is kind of like playing pinball with the face of the pinball machine covered. We can't see what's going on inside the game, but we shoot a ball in there, and we might hear some things happen, and we might see some lights light up outside, and then we see the ball come out somewhere else. And that's all we can see, and we have to guess what happened under the covered sheet of the game. We have to make some good, educated guesses. And since only one alpha particle came back in 1,000, what's up?
Hands-on stuff going on. Some pictures of something here.
Sure, you want to see our universe?
Sure.
All right, guys, I'm going to show her the universe. Let's show her our solar system. It's like we're taking a break from
Oh,
This is what we did all day yesterday. This is my new toy.
Awesome.
So Einstein, the theory of Einstein's general relativity is that space and time are not separate things, but they form one thing that is kind of like a flexible sheet stretched across a frame. So like this.
Okay.
And that everything that has mass puts a bend or a warp in that sheet.
Okay.
And the bending and warping is why gravity does what it does. And so that's like the sun in our solar system. And these are like the planets. Oops.
That kind of
Yeah, that planet's a road planet. We took it off and didn't find it over. So you get planets that go around this because of that bend in space-time.
That's awesome. I should get some video of that.
And this can demonstrate many things. You know, some people wonder, why do all the planets in our solar system go one direction? Well, at the beginning of the solar system, I've got green. You go that way. I'll listen. At the
Really
beginning
should
of
do
our
that. Should video of that.
At the beginning of our solar system, yeah, you can listen. When the solar system was first starting, things were going in all kinds of different directions. And there were just lots of bits of rock and planets going different directions, and this is what it looked like. So as they're going around, eventually they start hitting each other and falling out of orbit, and eventually you'll end up with See if it'll happen.
That's pretty good, actually.
But eventually it'll happen. It'll crash it, so eventually, here we go. Eventually things are only going in one direction. Right? Let's do it again.
Great.
As they collide, they essentially get rid of everything except stuff going in one direction. Is this going to collide? Oh man! The one in the first.
It's pretty cool.
But eventually, over time, you'll only get things going in one direction. And sometimes you can get 3 or 4 of them going in one direction, sometimes not.
And that's why all the planets in our solar system go in one direction.
Now they're all in one direction.
And that would have been a $2.
That's right. Yesterday we were playing with this and we started thinking of casino games we can make
Later.
for making money. This could be like, this could be 3-dimensional roulette. So let's make a solar system. So you can actually, if you're really good at this, you can make a solar system with different planets going around all at one time like this. Yeah, that's a really confused solar system. You need some serious tidal.
You, good work.
You're gonna have some serious tidal forces between the planets there.
Awesome. Thank you.
This is what we do when we're sick and tired of doing calculating.
Yeah, this is a lot.
I just cleaned up my 3D printer where it didn't have a printing ability.
Oh, yeah. I need to do a story on that too. And on the summer camp.
The summer camp is just about finished now. We've got our tuition waivers, so we've got our posters. Only the last thing we're trying to figure out is if we can get some materials that we collected. So I'm very close to being finished. Next week we should be able to do it.
Awesome. Sounds good. All right. Thanks, you guys. Sorry to interrupt your class. I thought once I was up here taking pictures, I'd seen you back here too.
More fun than class.
All right. Have a good one.
They almost all named it every other on that last one.
Yeah. All right.
Here.
Okay, sorry for that delay there. We had to do a little bit of public relations. So anyway, the reason that this is such an important experiment is exactly what you said, is that this was one of the first experiments done in science that was an indirect measurement, where you couldn't see anything that was actually going on. You could only see indirect things. It was all secondhand information.
What was his detector made out of?
His detector was essentially just a screen of luminescent material that would luminesce when a charged particle of high energy hit it. So it was kind of like a film. So that would glow. I probably made, I don't know exactly what it was made of, but probably silver nitrate. So that it would kind of like old photography equipment. So it would glow when something, a high energy particle hit it. But they discovered essentially that 1 in 1,000 particles would bounce back, and that's how they were able to say, well, the nucleus must be about 1,000th the size of the atom, because of that. And later on, they did more experiments where they studied the angles that things came out, and they were actually able to really figure out the size doing geometry of different kinds of atoms. And this became a kind of its own science. Eventually, people were using X-rays, very short wavelength light. Right over on that 1955 poster, they actually discovered DNA. The image for the DNA is over there somewhere. I think, is it that one or is it another one? Anyway, they made diffraction patterns and were able to discover that DNA is a molecule with the helical structure that we know that it has now. But the reason we know that it's a helix is not like in Spider-Man where they put it under a microscope and they actually see this helix rotating in the microscope. That's not what it's like at all. The only way you can see that actually is to use a particle diffraction and watch how particles bounce in there. In the case of Watson, Crick, and Rosalind, they used X-rays to do that, X-ray photons, and did a diffraction pattern with that. And it's all secondary stuff. And believe it or not, that's very similar to what's going on with our image at the beginning of this chapter, where you see the big face of the fly. That is actually not a direct image either. That is actually a diffraction image. It's actually an indirect image, and a computer makes an image out of it, or you can make an image out of it directly on film. But it's not a light image. It's a indirect detection image. So anyway, this was the beginning of detecting these things that we can't see directly in some kind of experiment indirectly. And it was also part of the beginning of quantum physics. Quantum physics is actually not as mysterious as it sounds in one way, and it's more mysterious than it sounds in other ways. In one way, quantum physics literally just means that we're going to be studying things, matter and energy, as individual things, instead of matter and energy as continuous things. For many, many, many hundreds, even thousands of years, everybody just assumed that the universe was made of a continuous substance everywhere. There's continuous things everywhere, that matter is just a continuous flow of stuff, and that you could chop it up and chop it up and chop it up, and you would never find a smallest piece of this matter that couldn't be chopped up. Eventually, people started to think, well, maybe there is this smallest piece, and it wasn't even eventually. I mean, 400 years BC, Democritus, the philosopher, thought that matter was all could be chopped up into a smallest piece that couldn't be chopped up. But he was one of the first and one of the last of his time that thought that. But later on, we started to see more evidence of this, and we started to understand that this might be the case. So when science was being done in the late 19th century, early 20th century, and we started to see even more evidence of this, scientists started putting these things together into a single theory to try to explain how matter and energy behave at very small quantities. So it's important to realize that quantum physics really only applies at the quantum level, at a very, very small level. The quantum effects wash out or are not noticeable at larger scales. Like in our everyday life, we hardly notice these effects. We never notice them. It's very similar to the effects of relativity. Relativity you only notice if you're going close to the speed of light. Well, quantum mechanics you only notice if you're looking at very, very, very small objects, like atoms and smaller. So we're going to start off with this guy, Max Planck, to say his name correctly.
What's the smallest part that we know of right now?
We'll get to that. That's a good question. We'll get to that eventually. I mean, to make it very simple, the electron. There are things that are technically maybe smaller, but the electron is so small that we cannot measure its size in any way, indirectly or directly. It is considered to be a particle with absolutely no volume, no size, but it does have mass, if that makes any sense. It's considered a point particle.
1.67 times 10 to the...
That's its charge. Its mass is much smaller than that, 9.3 times 10 to the minus 31 or 35 or something like that.
Yeah, it's going just
But its size, its length, its radius, its volume, it is unmeasurable at this point. We have some theories about it, but I don't know that anyone's ever measured. Anyway, the point is that it's a point particle. The point is that it's a point. Okay, so moving on. We start off with Max Planck. Max Planck. Max Planck was doing some experiments with thermodynamics. In thermodynamics, there is this idea that light and heat are related to each other. So if you heat up an object, if you make an object hot, it begins to glow. And when it's just warmish, it glows kind of in the spectrum that has low wavelengths, so long wavelengths, low frequencies, long wavelengths. So something that's just warm just glows with it might it might give off a little bit of radio waves, it might give off a little bit of infrared, it might even give off a little bit of microwaves, but they're fairly long waves. And the hotter it gets, the closer and closer it gets to the blue end of the spectrum, or the ultraviolet end of the spectrum, or even maybe into the X-ray spectrum. The hotter it gets, the shorter the wavelengths get. And there was a problem with this theory. And the problem with this theory was that you can get as hot, there is no end to how hot something can get. But there is an end to the wavelengths. Because if you're getting hotter and your wavelengths are getting shorter, what's the limit to the wavelength? Zero wavelength. Wavelengths, if you're going down in wavelength, they don't go negative. You can't make a negative wavelength. So there's a limit to the wavelengths. It's at zero. But there's no limit to temperature. Temperature can get as high as it wants to. And so there's a problem with this theory. In one end, you can go infinite. The other end, you can't. And so it's called the ultraviolet catastrophe, this idea. And that is that as something gets hotter and hotter and hotter, in order for this theory to hold up, it must get infinitely, the amount of light coming out must be infinite in intensity, because it can't keep going towards zero. I mean, it just gets closer and closer to zero, but it can't go beyond zero. So it has to increase in intensity for that energy to make up for that. And it does that. As it gets hotter and hotter and hotter, and you can see right here, you have something that is not very hot, 3000 K, which is red hot. I mean, it's glowing red. It's glowing in the infrared. This peak is out here in the 1900-ish. So that's infrared. As it gets hotter, around 4000 K, it starts to glow yellowish, greenish, and that is, pretty hot. As it gets at 6000 K, it starts to glow in the blue and the ultraviolet end of the spectrum. And that's when it starts to look white. When something looks white hot, it's not actually white, it's actually just an intense ultraviolet, which our eyes can detect, but they don't see it as a color. They just see it as a really bright white light. But as it gets hotter, this peak starts to grow taller and taller and taller, but it doesn't shift very much. If you're out here and you're a star that's not glowing, that's not super hot, or you're a planet that's not super hot, you're giving off microwaves and radio waves over here. But over here, and you're not very tall peak, but as you get closer and closer to these really hot things, it just starts to climb upward and it doesn't shift over here very much. And this is called the ultraviolet catastrophe. Eventually you'd reach an infinite amount of ultraviolet light or an infinite amount of X-ray light, but there is no availability for infinite amounts of energy. It's just not allowed in the universe. It's never been observed and it's not allowed. And so this theory was breaking down and people were having troubles with it until Planck came along and started to study these peaks, and he discovered that the peaks, that the frequencies were part of the energy more than the intensity was part of the energy. And he said, what if frequency is more related to energy than intensity? If it is, then shifting just a little bit frequency can give us a big shift in energy. And that would explain this theory better. And this was essentially the end result of his theory, is that if you have a light with a frequency f inside of an oscillator, and so in this case, he's specifically talking about essentially kind of things that oscillate back and forth, like antennas or electrons in an atom or things like this, then the energies are going to be quantized by the frequency, which means that each frequency is going to have its own energy of light. And that the energies of light are going to be dependent on those frequencies. And it held up. It actually explained what was going on rather than the theory that said we were going to have infinite amount of intensity. Because what was going on was that you were getting certain size peaks at certain frequencies for certain temperatures, and it didn't make sense according to the thermodynamic theory. The thermodynamic theory said you should just be able to keep going up in temperature, and this thing would just crank up to forever. But in real life, it didn't go to infinity. It limited itself to certain values. And those certain values could be predicted by Planck's theory. Planck's theory did have this constant that he had to throw in to make it fit the data, just like every scientist has to do. And it's a very, very small number, 6.626 times 10 to the minus 34 joule seconds. And because it's a very small number, that implies that this effect is most prevalent with very, very small things. In the end, what he discovered is that the energy is equal to the Planck's constant times the frequency for any frequency of light. For any light out there, the light at any particular frequency comes in this amount of energy. Comes with this amount of energy. What does that mean? Practically speaking, what it means is that if you go out and measure light, that it's 500 nanometers, and you measure the energy that's in that light, whatever it is, a flashlight, or a light bulb, or a laser, whatever it is. You measure the energy in 500 nanometer light. The amount of energy that you measure will be an integer number of this number right here. It's kind of like having a box full of marbles, and every marble in there is a full marble. There's no half marbles, no quarter marbles, and that bag represents how much energy you have. You can only take it out in certain amounts, and you can only put it in certain amounts for any given frequency. That means that light exists as a particle. Light is a particle. It's a thing that has a certain size to it. The size is not a physical size except in its wavelength. Its wavelength is a physical size, but it doesn't have like matter in it that can be measured, volume or anything. The size of light is in the amount of energy that it carries. So light comes in little packages of energy. For one particular frequency, it comes in a certain size package of energy, and you can have 50 of those packages or 500 billion of those packages, but you can't have 50.6 of those packages for that particular wavelength or that particular frequency. This is the quantization of light. Light exists as a particle, and it's a particle of energy. This particle of energy we later call a photon, and he was not the only person to discover this. Einstein also discovered this, but in a different way. The way that Einstein discovered this was with one of his papers in 1905. He wrote 5 papers in 1905. One was about this really kind of boring thing, which he won a Nobel Prize for, which is what I'm going to talk about now. The others were about relativity. But his most boring and least impactful paper of that year, he won the Nobel Prize for. And he was explaining a particular thing called photoionization, or the photoelectric effect. In the photoelectric effect, you shine light, like ultraviolet light, onto a metal, onto an active metal, and electrons will come out of the metal. But it works really, really well if you get that light to a certain frequency. So if you have light that's at 400 nanometers shining on this, at the certain wavelength and frequency, 400 nanometers shining on this metal, you might get a few electrons out. But if you increase that frequency or lower the wavelength down to 396, you might get a whole bunch of electrons out. And then you drop it down to 395, and then you get less again. and then you drop it down a little bit more, a little bit more, a little bit more to like maybe 340 or something, and then a bunch of electrons come out. And then you lower it down, and then it don't come out again, but just get a few. And Einstein described this in two ways. People already knew that light had energy, so they figured that the light hitting the metal, the electrons in the metal were absorbing the energy, getting too energetic and jumping out of the metal. That they knew. That they understood. But they didn't understand why at certain frequencies more would come out. Right? And Einstein started to explain that using in his paper. And again, it comes down to that certain wavelengths have certain energies, give photons of certain energies. And he said that these waves coming in of light are actually not just waves, they're actually packets of energy. And at certain wavelengths, you get certain size packets, which are just the right size packet for certain electrons. And some electrons need that certain amount of energy to jump out. And once you hit that certain wavelength, each one of those packets is just the right amount of energy, and a bunch of electrons grab onto them and jump out. And so this idea of the quantized light particle, or the photon, was a big thing. It was a big discovery. Einstein explained it. Max Planck quantified it. He was able to put this equation to it. So if you want to measure the energy for any photon of light, you take Planck's constant, 6.63 times 10 to the minus 34 joule seconds, and multiply by the frequency of the light. In this case, 10 to the 14 hertz, which is an infrared frequency. And it gives 6.63 times 10 to the minus 20 joules of energy for that particular photon. That wavelength of light comes in packages of this size, 6.63 times 10 to the minus 20 joules. This also explains something else that was happening. According to Rutherford's experiment, atoms were this nucleus in the middle with electrons orbiting outside like planets. Well, if they were orbiting outside like planets, and we believed that it was planetary in nature, then those electrons could orbit at any radius that they wanted and at any speed they wanted, just like we did over here. Which would mean that they could have any energy at all. However, when people were going in and removing electrons from atoms using usually electricity, they discovered that electrons only popped out, just like in Einstein's experiment that he explained, at certain energies for certain atoms. So, for example, if you look at oxygen and you ionize oxygen, take the electrons out of oxygen, all these little bright lights represent the frequencies of light that will come out of oxygen, which essentially tells you where the electrons are existing, in what orbits they're existing in, if they were planets. And each one of these is associated with a different energy. If you did this with electricity, you would notice that as you raised up the electricity, you would get electrons out, and then as you raised it up a little more, you wouldn't get any out. Then you raised it up a little more, you get electrons out, and then you wouldn't get any, and then you would get some, and then you wouldn't get some, and so on and so forth. They would ionize at these specific energies, which suggested that the electrons could only be in certain orbits at certain radiuses from the nucleus. And that was weird, because why couldn't the electron be somewhere in between two orbits? There's nothing that would prevent it doing that, according to Newton's theories. But here it is. This is the way oxygen always looks. There's nothing in between. There's just these bright lines where those things live. And some of them are brighter than others, which suggests that some of these orbits are much more populated than others. They're much more popular, you could say, right? And so they started to come up with a new model for how the hydrogen atom worked. Let's see if we can see this one here. See if this one pops up for us. Maybe not. Doesn't always work. Here it is. See if we can get it to open. That's the real trick. Yeah, okay. So here we're gonna do one of these experiments. We have our hydrogen inside of this box, and we're going to give it some light here. We're gonna shine some light on it and see what happens. turn on the gun. So if we shine some light on it, white light, that's not helping. Yeah, if we shine white light on this box of hydrogen, what happens is that sometimes, every once in a while, we get certain light back that bounces off of it. But it's only certain lights. We get a blue one, we get a purple one, and we get one more. But if this was the atom that that we first thought it was, if this was like planets going around, we would get every kind of light coming out of here. But the only kinds we're getting a lot of purples out. Every once in a while, a purple bounces out, but like that one. But and every once in a while, we get a blue one out, a greenish blue one, like that one, but it's not coming out yet. If we do a single color of light, all purple, then we get some purples bouncing out, or all ultraviolet rather. If we come up here into the color spectrum, see if we get anything. Only at certain places will we get anything coming out. Trying to find it. Can't find it. If we had more time to mess with this, though, we would find that there were certain colors that we'd see popping out every once in a while. I think there's one in the red. Anyway, the point is that they discovered that these atoms do this. They have this behavior where, oh, I should have shown the spectrometer. That's what I should have done. Let's do that again really quick. That'll make it easier. I didn't see that till the very end. Show spectrometer. There we go. So if we do white light, we turn it on here, then we start to get some things bouncing around here. We get one out here in the UV. I want more light. Come on, I want this to happen faster. Got one over here at about, what's that? Where? Oh, yeah. There we go. So we're getting some over here in the UV. We got one in the blue. We got some in the red. One over here, and a lot over here. Right around 92, right around 450 maybe. Right up here around 650 something. So, but we've got just these certain things, these certain lights coming out when we shine light in. If we go monochromatically, we start at 94, we're going to get we start at 94 or 92, we're going to get a bunch of these things building up over here. 92-ish, 94 it turns out it's where it's at. Because you can see it really climbing there when we put it to 94. When we move it across the spectrum, we don't get anything until we get to about 4, I don't know where that's at exactly, 430 maybe. Can't tell where it's at.
Yeah, that is what I was saying. It would be like 505.
Should be at 430 something, I'm guessing. 440 maybe. The red one, which is at just above 650. Man, I just can't find it, can I?
Start at 665 and work your way down.
And this is actually really quite accurate because this is what happens with these is that you have to get right on there. So doing these experiments takes quite a bit of things going on. If you look, and so right now we're looking at, if we look at this is the model that Rutherford thought he was doing, right? This is the plum pudding model or the cake model, and then the classic solar system model, which the classic solar system model can't exist. Then this is a later model, and a later model still, and a later model. We'll take a look at these ones later. But anyway, what they were discovering at this time was, though, is that electrons only had certain energies inside the atom. And so not only was light quantized, but the energy levels inside of the atom were quantized. And atoms was quantized. So atoms came in little parts. Energy inside of the atom came in little parts and little packages. Light came in little packages. And they were just starting to discover that all this stuff interacts as one thing interacting with one other thing instead of a wave interacting, like a wave of water interacting with all kinds of things. Instead of the wave of the water just pushing the beach up the slope of the beach there, up the slope of the strand, it's like an individual water molecule pushing an individual grain of sand up a slope. And you have to treat everything like that in order to truly understand what's going on. And that's what they started, that's how they started to view the world, the subatomic world, after they started making these discoveries. And that is essentially the beginning of quantum physics. Let's see how much more we have here. Quantization of energy, photoelectric effect was what we just did. So we're gonna move on to next time. Wait, we still have an hour left, right?
Yeah.
We're good. Never mind. I'm like, man, that time went by quickly, but I was looking at the wrong time. So we're good. We can keep going. So this is quantization of energy. So let's move on to the next stuff here, which is the photoelectric effect, which we just talked about. Goodness, what's going on with my book? It's stuck. Okay, so photoelectric effect, which we just talked about, where you have light flashing onto a metal, and you get light coming out. Well, in the classical theory, what you should get in classical theory is as you increase the brightness of the light, you should get an increase in the number of electrons coming out, and the energy of the electrons coming out. That's what you should get in the classical theory, but that's not what happened. What really happened in the experiment was that as they increased the, and they have a photoelectric effect in here. So let's do this one. I probably have these saved 100 times on my computer, but whatever. So what they expected is as they made the light brighter and brighter and brighter, and they did this in a vacuum. So here's the metal that they're going to shine their light on. Here's the light they're going to shine on it. And then they put a battery across it. So they turned on a battery here to some voltage, and as electrons came popping out of here, then the electrons would jump across to the other side because they'd be attracted to the positive side of the battery, essentially. So the idea here is now to increase the intensity and see what happens to the number of electrons coming out. Well, you have one electron coming out, and then you have, more electrons coming out, and that makes sense. So, sure, okay, that's what we expected. What we didn't expect is this. So we turn down our light to maybe 20%, and now we start changing the frequency of the light. So at 100 nanometers, we have regular electrons coming across. And then as we move to the right and lengthen our thing, we have it's an increase and then a decrease. And then an increase, we get a decrease again, and then an increase again. And we start, and then we have almost none right there. Where was that? Right there? Almost nothing right there. And then a whole bunch again. And then nothing. And then nothing. And according to our theory, this shouldn't have done anything. changing the frequency shouldn't have done a thing. It should have just been about intensity. But here we can see that we get all kinds of variation. As we're out here towards the ultraviolet at this end, we tend to have more electrons, but every once in a while we have fewer as well. It goes up and down a little bit. But we generally have more in the ultraviolet. As we get towards the visible, even though it's the same brightness, same intensity, we have less, but every once in a while we hit this spot where we have more coming out again. Right? And this did not make sense. But again, Einstein came in and said, well, it's the frequency of the light that determines the energy more than the intensity. Intensity does have something to do with energy, because intensity essentially tells you how many packets of energy you have coming. Whereas the frequency tells you how much energy is in each packet. The intensity tells you how many packets you're sending. Right? So it's kind of like light. For every frequency of light, there's a different size bucket that it's poured with. For the higher frequencies or the lower wavelengths, so out here towards the UV and X-rays, the buckets are bigger. And so each photon of light is a bigger bucket, it has more energy to it. Intensity is how many buckets are you going to dump. If you increase the intensity, you're getting more buckets per time, more buckets per second. Right? Whereas this determines how big that bucket is. So measuring energy is not always the best way to measure intensity, for example. You can't measure intensity by measuring energy, but that's what we used to think we could. Because energy is not just a function of intensity, it's a function of intensity and wavelength. So anyway, and it's different for every metal, they discovered. If you put in zinc there, the electrons come out at different wavelengths. It's different wavelengths where they come out with more electrons. Right here you can see with zinc, nothing's coming out. With sodium, electrons are coming out. With copper, nothing's coming out. You change the intensity all you want, nothing's coming out. You have to go and find a frequency where electrons come out. It's different with every metal. They have different places where they tend to interact. Some of them don't interact at all at these lower frequencies and these lower frequencies, longer wavelengths, and you have to really get them out here to the ultraviolet to have it happen. So they learned a lot of things with this, not just about how electrons are quantized or how atoms are quantized, but how different metals are related to each other as well. We haven't done, let's do an example here really quick. So here we have calculating the photon energy and the photoelectric effect of violet light. So what is the energy in joules and electron volts of a photon of 420 nanometer violet light? We use Planck's equation for that, E equals HF. So that's pretty simple. And then we're given the wavelength, so we have to calculate the frequency using speed of light over wavelength equals frequency. That's pretty easy to calculate in the end. Converting to electron volts, 1 electron volt is 1.6 times 10 to the minus 19 joules. So it's the same as the charge of the electron is the same as the conversion from joules to electron volts, and that's not a coincidence. But anyway, for part B, to find the kinetic energy, you're going to take that energy that we had, I would just take it in joules, and calculate the kinetic energy. Or do they want, let's see here. Actually, they wanted the kinetic energy in electron volts. So in this case, we have to calculate the binding energy. Now this has something to do with what Einstein did. Einstein discovered that there is a binding energy, which is how much energy is holding the electrons in the metal. That's the binding energy, and that's the amount of energy that you had to apply with the light. That's the energy of the light coming in that released the electrons. And then you have the kinetic energy of the electrons coming out. That's related to how fast they are coming out. And the difference between those two would be, the sum of those two would be the total energy of the light that we shined on it. And so if you want to calculate that kinetic energy, you have to take the light, the energy of the photon coming in, which is h times f, subtract off the binding energy, and then calculate the kinetic energy. And in this particular case, they tell us the binding energy of the electron is 2.71 electron volts. That's also called the work function. So, as they started to put this stuff together, they started to classify things, organize things, and understand things a little bit more. And now we've got this table of energies associated with different photons of light or different wavelengths of light. Here's our visible light range right here, this tiny little band from the edge of the infrared to the edge of the ultraviolet. Goes from about 400 nanometers to about 700 nanometers in that range. And those have energies in electron volts of something like, I don't know what it is. I want to say it's like 1 electron volt or something like that. Something in that range. They actually calculate one here somewhere. Let's see. So if you divide, yeah, it's about that. Yeah, it's right around. It's right. It's just a little bit more than 1 electron volt is the energy that we see in the range that we see in is right about 1 electron volt, a little bit more. But you can see as you go out here towards the longer wavelengths out here, which is the lower energies, you get definitely lower energies. 4.14 times 10 to the minus 13 electron volts for long radio waves. Very, very tiny energies out there. And then out here it starts to get really, really, really big. When you get to the ultraviolet, you immediately get into the kilo electron volts and then the mega electron volts for X-rays. And then for gamma rays, big mega electron volts, even to giga electron volts. And of course, as we're going out this direction, we're getting smaller and smaller and smaller, closer and closer to zero wavelength, right? So the frequency is going up, the wavelength is going down, and the energy is just rocketing upward as you get shorter and shorter and shorter. Excuse me. Another thing that was learned is that energies, there are lots of light, there's lots of light given off by lots of different things. And these energies can be also measured. We measure them in electron volts and characterize them. So molecules, as they rotate, they twist and turn and rotate and other things, they can give off light, and they give off light in the 10 to the minus 5th electron range. So 10 to the minus 5th electron volts is right about here. That's the microwave range. And that's exactly why we can heat up water with a microwave. Because a microwave is a light that has a particular photon of energy that is about the same as the energy that makes water rotate, makes water vibrate. So if you can get water to vibrate and get it to give it that perfect amount of energy, it will absorb that energy and vibrate and heat up. The vibrational energies of molecules are about 0.1 electron volts, so that puts us right in here. Molecules vibrate right about in the range that we can see, pretty close. And many of them actually do vibrate in the range that we can see that, and that's why we can see things, because things are made of molecules all around us, and they're vibrating and letting off these energies that we can see. Energy between outer shells and electron atoms, right around 1 electron volt. That's also why we can see, because things are made of atoms. And electrons in the atoms are going up and down in their electron configurations, in their different states, and they're releasing light that we can see. Binding energy of a weakly bound molecule, about 1 electron volts. So a weakly bound molecule, again, we can see 1 electron volt energy. So if it does that, if it releases that energy, we can see it. Energy of red light, 2 electron volts. So that's, again, we can see that. Tightly bound molecule, 10 electron volts. We can't really see that. That's a little bit out of our range, more in the ultraviolet range. Energy to ionize an atom or a molecule, anywhere from 10 to 1,000 electron volts. Here's one of the first X-ray images taken by Röntgen. This is his wife's hand, and he put some instruments on it, and also she's wearing a ring. But this is just to demonstrate that a very high energy light has slightly different abilities than low energy light. High energy light, which are X-rays and gamma rays and ultraviolet out here, they have different properties. They can do different things. Instead of hitting something and exciting the atoms and the electrons in your hand so that you can see the hand, so you can see the skin, it goes right through those ones. And it doesn't make anything do anything. It doesn't cause any kind of reaction. It just goes right through it. And then if you put a piece of film behind it, you can see where it didn't go through as well. It doesn't go through metal quite as well, and it doesn't go through bone quite as well. But it goes through skin really well. What's that?
There's a gem in the ring that you can see the outline of.
There's a what?
There's a gem in the ring. It's dark.
Oh, yeah. Right there.
Exactly.
And you can tell that it's probably not a diamond because of the cut. Because 100 years ago, diamonds were not nearly as popular as they are today. Why are diamonds expensive? Not because they're rare, because they're popular. Well, they're useful, but that's not why they're expensive either. They're expensive because they're popular. Diamonds would not be nearly as expensive. I mean, there are many, many more rare gems out there. Natural rubies, natural pearls are far more rare. A natural round pearl is far more rare than a diamond is. But the price of diamonds is really high because they're popular and they're controlled by just a couple of different countries and companies. So it's kind of interesting. Okay, it's conservation of energy. So conservation of energy is still in effect when we enter quantum mechanics. But we have to think of it in different ways now, because now we know that energy exists as a quantum thing. It exists in packets inside of the frequency of light as well as the intensity of the light. So we have to count up the energy differently. So there's lots of different things we have to consider. When it comes to X-rays, creating X-rays, that is something that had to be considered because they didn't really understand what was happening with X-rays. What's happening with X-rays, you create a stream of electrons at high energy electrons, high speed electrons, and you accelerate them towards a metal target. And as these electrons impact this target, they get essentially absorbed into this target, and then the target releases X-rays. And the energy, the kinetic energy of those electrons becomes the quantized energy of the X-rays. And the really interesting thing is that different metals release different X-rays. And they don't release X-rays just of any old frequency. They release X-rays of specific frequencies at specific intensities for that particular metal. So you can actually tell exactly what metal is in any particular X-ray gun or X-ray tube just by looking at the frequencies of the X-rays. Now I've got some X-ray tubes here, 2 different X-ray tubes. This one, let me turn on my camera so everybody can see what I'm doing. This X-ray tube is a very small one. They're both very small, actually. This one has what is called a transmission target. So the X-ray gun is at this end, and it's inside of this metal tube. And on this end is where the target is, and it's made of a silver-coated window, a beryllium window, which is beryllium. X-rays go straight through beryllium, don't even see it. But it's coated with silver, so that the silver is the thing that is going to make the characteristic X-rays. This one is this one is more like the tube we just saw in our book. It's a tube that is at an angle here, and it's made of copper. And then there's a beryllium window here for the X-rays to come out. and the electron gun is down at this end again, and you fire the electrons down, and they hit the copper, and then they come out this way. They come out 90 degrees to the electrons, and those are some tubes that I worked for a company where we made these tubes and tested these tubes. I was mostly involved in the controlling of the tubes and the powering of the tubes. But those are some X-ray tubes we made. That type of X-ray tube is the kind that we were building those for NASA, actually, and those were for the NASA Mars rover. So they're very, very small, very, very low power requirements, which is nice. But the idea there is that kinetic energy of those electrons gets turned into light energy. It gets converted into X-ray energy emitted by the target when the electrons slow down. Now this is what it would look like. This is what your X-ray spectrum would look like coming off of some particular anode material, a metal that you're hitting these electrons into. You're going to have this kind of curve down here, which they call the Bremsstrahlung, which literally means breaking radiation in German. And that right there are X-rays that are created as the electrons slow down in the metal, as they come to a stop in the metal. And then you have these two peaks here, and sometimes it's 2 peaks, sometimes it's 4, sometimes it's 7, whatever it is, depends on the metal. But these peaks actually are electrons that were kicked out of their orbits by these incoming electrons that were hammering the anode. They were kicked out of their orbit into some other orbit, and then all the other electrons kind of fell down into those orbits and released these X-rays. So these are high energy X-rays that came out because of disturbances in the orbits of the electrons in the metal atoms. And they're at specific frequencies because those electrons are at specific energy levels. And so they only release certain energies of light. So here we can find the maximum energy in electron volts of X-rays that can come out by electrons that are coming through a potential of 50 kilovolts. How do we do this? Well, if it's going through 50 kilovolts, we can use the voltage and the mass of the electron to determine the kinetic energy of the electron. Because you can get energy from the charge of the electron and the voltage. Charge times voltage is energy. And then you can set that equal to 1/2 mv squared and find out the velocity. Or you can just say that's going to be my kinetic energy either way. You don't have to do the multiple calculation to undo and then redo what you just did. But anyway, you can figure out the energy from the charge of the electron and the voltage of the electron. And then that has to equal the maximum amount of energy you can get out from a photon. Okay? That essentially will equal the X-ray that's on the right end of this, the top end of this frequency spectrum. Then all these other ones will be ones that were released that were also released, but the maximum one is the one that's on this end of the Bremsstrahlung. So we calculate that. This is the equation. This is the energy of the photon, frequency times Max Planck, so Max Planck's constant, and then charge times voltage, which gives us the kinetic energy of the electron coming in. So charge times voltage, we know Max Planck's constant is 6 point, I can't remember what it is. Whatever it is, times 10 to the minus 34, 6.314, 6.14, 3.6, I can't remember what it is. Whatever Max Planck's constant is, we're going to divide it on both sides, and we're going to solve for the frequency. And when we solve for the frequency, actually they don't even want the frequency. They just want to know what is the they want to know the energy in electron volts. So we multiply 50 times 1.6, and then we do the conversion. Notice that the conversion and the charge cancel out, and we end up with 50 kilo electron volts. So what's the moral of the story? We started with 50 kilovolts and an electron. If an electron is in a 50 kilovolt field, or 50 kilovolt potential, it's going to have 50 kilo electron volts of energy. This is why particle physicists use electron volts because they're often using electrons. So it makes it easy to calculate the energy if you know the voltage. And voltage is easy to measure. You just measure the voltage. All right, I've got 20 volts here, so I'm going to have 20 electron volts of energy in my electron. Oh, I've got 50,000 volts. I'm going to have 50,000 electron volts of energy in my electron. The voltage essentially becomes the energy in electron volts for an electron. And if it's a proton, it's the same because a proton is the same charge, just opposite sign. But if you have something that is doubly charged, then you can have twice as much. So if you have, for example, if you have a helium ion, which has a charge of 2 electrons, has twice the charge of an electron, but positive, then you put it in this 50 kilovolt field, it's going to be 50 times 2, so it'll be 100 kiloelectron volts. So it becomes very easy to keep track of your energies just by keeping track of the charge and the voltage, two things that are very easy to measure. So here's another example. We have a short wavelength ultraviolet, sometimes called vacuum ultraviolet. And we want to calculate the photon energy in electron volts for the 100 nanometer vacuum ultraviolet. So here we have our equation equals the Max Planck constant times F, which we're going to convert F into C over lambda so that we can use the wavelength. We just plug in our numbers, C over lambda here, and we get 12.4 electron volts. Now H times C turns out to be 1,240 electron volts nanometers, and that's why they put that number in there. And that's a number that is well known to particle physicists. Max Planck's constant times the speed of light is always 1240 electron volts. So just something that you should know. And you'll want to use that because it's much easier than plugging in two numbers. It'll work either way. Okay, so here's the electron volts for visible light, 1.63 to 3.26 electron volts. Visible light to red, red to violet. So why do these red colors and yellows and greens fade before the blues and the violets when they're exposed to the sun?
Because they're absorbing more high energy particles.
Well, not necessarily absorbing more, but when they do absorb high energy particles from ultraviolet, it has a more deleterious effect on them because of their color. They emit what? Deleterious? Yes, I can. Detradeleterious? No, it's deleterious. I was going to say detrimental, and then I changed to deleterious. Yes, I can. Anyway, the point is, things that have the color of an object actually tells you something about the molecule, about the strength of the bonds in the molecule. Things that are colored more towards the red end of the spectrum tend to have the strength of those molecules. Those bonds in those molecules tend to be weaker because they're giving off these red colors that is related to the strength of the bond in the molecule. And so ultraviolet light that's coming from the sun has an easier time breaking those apart. Things that are blue or closer to the blue end of the spectrum have stronger ones. So color of things has a tendency to show us something about the materials. This is also why you can look at a planet, well, it's related, is why you can look at a planet with a telescope and detect all the different frequencies coming from it or not coming from it, and determine what's on that planet. You can determine what the planet is made of, essentially. So it's kind of a similar thing. If you remember on the last experiment we did with the, let's see if it's still here. We did that online experiment with this guy right here. With one metal, sodium, we could get particles out using just about any color of light. But sodium is a very, very fragile metal, you could think of it as. Sodium is extremely active. You put it near almost anything and it's going to react and fall apart and become something else. However, you have things that are much more stable, much difficult to deal with. Try any light besides UV and nothing works. Platinum is a metal that is extremely stable. You have to really crank up the UV all the way out to those highest energies of UV to get anything out of platinum. It's an extremely stable metal. So also quite related to that. So in the end, we learned that low energy photons tend to be the photons that are associated with the longer wavelengths of light. So reds and infrareds and radio waves and things like that, those are low energy photons. And they have a tendency to do low damage to things, very little damage to things when they encounter them. Unless they're in high intensity, they can't really do much damage. Even at high intensity, they do less damage than ultraviolet or infrared, or ultraviolet or X-rays or gamma rays. The gamma rays and the X-rays, the high energy photons that are associated with short wavelengths, it doesn't take a lot of photons to do damage. You know, just a little bit of exposure to ultraviolet can do a lot of damage, can give you cancer, for example. And that's exactly what cancer is. Cancer is just damage that's been done to the DNA molecules in your body. When you do damage to DNA, it breaks apart the DNA and your body has to fix it. And when your body goes back and fixes it, sometimes it makes mistakes. And the more damage there is, the more likely it is your body is going to make a mistake repairing it. And so if you go out in the sun a lot and you spend a lot of time damaging your DNA out in the sun and your body's constantly having to fix it, there's more likelihood you're going to get skin cancer. If you spend a lot of time smoking in your life or around any kind of smoke at all, it doesn't matter if it's a cigarette smoke or smoke from a house or whatever, you spend a lot of time smoking, it damages your lungs. And the more damage you do to your lungs, and it doesn't have to just be smoking, it can be inhaling dust. The more time you spend inhaling dust, the more damage you do to your lungs, because your lung cells, the alveoli in your lungs, are extremely sensitive to things. And so if you're inhaling a lot of particulate matter, and particularly really small particulate matter that can really get in there and do damage, then your body has to repair it, and the more likely you are to get lung cancer. It's not just smokers that get lung cancer. They're the most likely targets because they put smoke in their lungs, which easily gets into the lungs, lung tissue. Doesn't matter what kind of smoke it is. If you spend a lot of if you spend a lot of time in your life doing damage to your intestines, okay, so cancer of the intestines is a very, very common kind of cancer, and it is caused by damage done in the intestines, usually by food, but often also by bacteria. So if you're in an area where you have a lot of bacteria that your body has to fight against in your intestines, or if you put food in your body that does damage to your intestines. What kind of food does damage to intestines? Well, there are certain proteins that do damage to the intestines. Protein from corn, for example, does damage to the intestines. And particularly when those corn proteins have been processed by an animal. So corn-fed meats have a tendency to do a lot of damage to the intestines. If you eat a lot of corn-fed meat, you're at higher risk for cancer. Corn-fed beef, corn-fed chickens, corn-fed pork, all of that is much more unhealthy for your body because it does damage to the intestines, and that increases your risk for cancer. And if you go to California, everything causes cancer. They put that label on everything. Because really, technically, almost anything can cause cancer. It just has to do enough damage to your body regularly enough that your body has to fix the DNA in your body, and then starts making mistakes. And then that DNA mistake propagates. It's really quite a simple thing in the end. Okay. Now, momentum. This is where it starts to get weird. How can something that has no mass be a particle? Well, we've decided that it's a particle because energy comes in certain amounts, certain sizes of energy, certain amounts of energy. Okay, fine. But in the theories that Einstein was going through and Max Planck was going through, they started to see that light, being a particle, suggested that light would have momentum. And that started to bother people, of course, because momentum has always been associated with mass. Momentum is equal to mass times velocity. If you don't have mass, you can't have momentum because momentum is equal to mass times velocity. But it turns out that light does have momentum, not just in theory, but it has actually been proven now. When something has momentum, it implies two things. First of all, when something that has no mass has momentum, it implies two things. First of all, it implies that that momentum is not necessarily tied to mass, that it doesn't necessarily have anything to do with mass. But it also implies that something that does not have mass can push on something that does have mass. Now that seems kind of weird, but it's actually true. So, how was this first discovered or first observed? It was first observed with comets. When a comet comes close to a star, the tail of the comet is following behind the comet like we always think it should, because we always think when something, is flying through the air and it has something coming off of it, the something that's coming off of it flies behind it. And that's just our experience. But in space, there's nothing to suggest that anything should come off a comet and leave its orbit, or leave the comet anyway, because there's nothing pushing stuff off the comet. However, as the comet comes closer to a star, it heats up and it starts to evaporate things off the comet. Usually comets are made of ice chunks, and so you get ice and dust coming off the comet, and it starts to form a halo around the comet. And as it gets close to the star, this halo starts to stretch out away from the star. And as it gets closer to the star, the tail always points away from the star, and as it's moving away from the star, which is actually this bottom part, the tail actually precedes the comet. The tail is actually in front of the comet's motion. And that really started to confuse people. And I believe, let's see, who was it? It was, they don't even show who it was that first came up with this theory. The first person that came up with this theory was about the same time as Galileo, I want to say. His name was, I can't remember his name all of a sudden. He was Dutch, I want to say. Was he Dutch? I can't remember. Anyway, is an astronomer from hundreds of years ago who came up with this idea that the sun actually had some kind of wind associated with the light. The light was so bright coming from the sun that it was like wind, pushing the tail of the comet away from the sun. And in a way, he was correct. It's on the tip of my tongue. Who was it that said this? Now I gotta know, so we gotta go find it. Solar wind, comet tail, solar. It was my goodness, doesn't show anybody who did this. It was They're not going to talk about who first discovered this. Are you kidding me? I can't remember who it was, but anyway, that's okay. We'll move on. But this idea that light can push on something that has mass was certainly known, or at least thought to be the case long ago, and now it is actually known. And the way to calculate this momentum in the theory turns out to be also related to Planck's constant. Planck's constant shows up in everything in quantum theory. So in this case, it's Planck's constant divided by the wavelength will give you the momentum, or Planck's constant. Let's see, that would be Planck's constant times frequency divided by c or something like that. But it's Planck's constant divided by the wavelength gives you the momentum. And now you can measure the amount of momentum that a photon has. And here they actually calculate the momentum of a visible photon of light, wavelength 500 nanometers, like green light. So you do this, and you get 1.33 times 10 to the minus 27 kilogram meters per second. That's a tiny amount of momentum. That's barely enough momentum to push on a proton. But it is enough momentum to push on a proton, right? So you have to have a lot of this light, a lot of light to push on things. And that's why it only really works for things that we can see, like a comet, when the comet is right next to the sun, which is the brightest source of light, for a long distance, right? So this is actually true. They've done the calculation for comets. But the really interesting thing is that Einstein combined together with another scientist named Bose, who was at Princeton with him, I believe. Maybe he was at MIT, I can't remember. But he was over there in those Ivy-covered colleges with Einstein at the same time. They came up with this theory that you could actually slow down atoms using light, because we know that they knew at that point that temperature or heat inside of something was caused by movement of atoms. So they said we could actually slow down the atoms so much using light, but the light would have to be the perfect wavelength, so it would give the perfect amount of momentum to the perfect atom. But you could slow down these atoms enough that they would actually get really, really close together, so close together that they would actually start to affect each other's behavior. They call this the Bose-Einstein condensate, which we'll learn more about later. And that was proven to be true. It was proven that you could use light to slow down atoms a long time ago, shortly after Einstein and Bose predicted this. But they weren't able to slow down enough atoms to make them behave, to change their behavior. But they were able to finally do that about 20 years ago, in the 90s. And that was the subject of several other Nobel Prizes when they created the first Bose-Einstein condensates. Here's another really cool application of this, and that is the solar sail. And we've actually been testing these in space now for quite a while. You can see a picture of one here in B. But we have the idea of a solar sail is that you have your payload or your spaceship or whatever it is, and then you deploy this huge mylar sail, which is essentially a big mirror. And then you point your spaceship away from the sun so that the sail is getting the full effect of the sun, and then you just let the sun push you, and it'll just keep pushing you as long as you can see the sun. And of course, the further out you get, the less the sun's going to push you, but it will still push you. You have to have a huge sail for the size of your spacecraft to get anywhere. But it does work. And so this solar sail here, you can see the size of it. You've got these 4 people standing underneath it. And it's this huge sail, and it's designed to push something that is really quite small, probably about the size of this computer or smaller. But the sail, like the size of a football field.
Sending a cell phone to Mars.
Yes, send a cell phone to Mars, exactly. But in principle, you should be able to reach much higher speeds because your acceleration continues and continues and continues without the need of internal fuel. So if you could start at Earth and travel all the way to, for example, Mars, you should be going so fast by the time you get to Mars that you could pull in your sail and keep going all the way out to Saturn and get there much faster than you could using any kind of rocket technology. The problem is, how do you slow down? You can't just turn the sail around and slow down like you can with a rocket because the sun will still push on it in the same direction. So you do have that problem. But if you're interested in a one-way trip, which or if you're interested in a two-way trip, and you can carry some fuel with you for slowing down or for stopping and turning around, then it's actually a very good thing, because a solar cell is not going to weigh very much. It's going to be very, very thin material. Mylar is a very, very thin material. So for even a sail this size, size of a football field or even bigger, you could pack that entire sail in something smaller than a small file cabinet. It just wouldn't take much. It's not going to take much space. But it's still a big undertaking for sure. But really quite cool. One of my favorite technologies. Very simple, very elegant. But you can also, the problem here is that when you start accelerating small particles using momentum, using light, small particles reach high speeds so easily because they're so tiny. Electrons are just so tiny. Then they start to become relativistic. So then you have to start thinking of them relativistically. So then you have to have relativistic photon momentum. Okay, so this starts to get really crazy. So this is how you calculate relativistic photon momentum. You include in your, let's see. Oh, so here's the relativistic part where you have E equals PC squared plus MC squared, right? So your energy is PC, and then your momentum is P equals E over C for photons. And this essentially tells you the momentum of an actual photon, because it's reaching the speed of light. And it's really just a solution to the energy equation. Energy is equal to momentum times C, so momentum is going to equal to energy divided by C. It's that simple. And you can check to make sure that it's valid by plugging it into the momentum equation for particles, and it comes out to be h over lambda in the end, so you're fine. But that's the equation for the momentum of light. You take the energy of the light, which of course is calculated by the wavelength, using the wavelength and Planck's constant, hc over wavelength, or sorry, wavelength times frequency. Planck's constant times frequency. That gives you the energy of the light, and then you divide it by c, and then you will get the momentum of that light. And each photon of light has a different momentum. It imparts a different momentum. All right, so photon energy and momentum. Here we calculate the energy, the momentum of a photon that has 2.48 electron volts of energy. So the energy is 2.48 electron volts. We convert that to joules. Divide by the speed of light, 3.0 times 10 to the 8 meters per second. And that has a momentum of 1.33 times 10 to the minus 27 kilogram meters per second. Notice that it's not very much momentum. But again, it's enough momentum to affect an atom, because that's right along the same. This is the momentum. This is almost the same as the momentum of a proton moving at 1 meter per second. So this momentum, if it was transferred to a proton, would speed it up or slow it down 1 meter per second. So that, that's significant for a proton. It won't affect us. We won't be walking down the street and the sunlight's not going to be pushing us around. But it will definitely affect protons. All right, so now we get into this idea that we're essentially what we're facing at this point is, how can something be a wave and a particle? If light is a wave, it behaves like water waves. But if it's a particle, it behaves like tennis balls. So how can a tennis ball be like a wave? And how can a wave be like a tennis ball? And we start having these arguments, how this can happen. But then somebody walks in the room and says, well, if light is a wave, but it's also a particle, then can particles also be waves? Like, can an electron be a wave? If light can behave like a tennis ball and like a wave of water, why can't a tennis ball behave like a wave of water and a tennis ball? Right? And people started to think about this, and they started to realize that actually the theory supports that. The mathematics says maybe an electron is kind of like a wave. It's not a wave like light waves. Light waves are a wave of electricity and magnetism waves, electricity and magnetism fields. But a particle actually might have some kind of wave behavior to it. And so we have to start thinking about that. So what happens? Here's the experiment. When we're doing waves, if you have some water waves coming in and it hits a wall, and you have two holes in the wall, then you're going to have waves coming out 2 holes in the wall, and those waves are going to interact with each other, interfere, and you're going to get some choppy parts and some non-choppy parts where the peaks add together and then the peaks and troughs add together, where you get destructive interference and constructive interference. And it's just like light. When you do this with light, they come in and you go through the 2 slits, you get bright spots, black spots, bright spots, black spots. But it's not that way with a machine gun. If you have 2 doors and you shoot a machine gun through 2 doors, you get bullets where the doors are. You don't get bullets between where the doors are and out here where the doors aren't. You don't get a diffraction pattern of bullets. However, if you do this with electrons, you do. If you have an aperture, 2 apertures next to each other, 2 little holes, 2 little slits, very small and very close together, and then you fire just gazillions of electrons at this wall, and out this other end you're going to get some electrons coming out of each of these holes. These electrons start to interact with each other in such a way that you get electrons building up in certain spots and no electrons building up in other certain spots that looks just like a light diffraction pattern. And you say, wait a second, how would the only thing that causes that kind of behavior is wave behavior. But electrons are particles, they're not waves, we know that. Well, light is a wave, and we've just discovered it's also a particle. So why not a particle being discovered that it actually also has some wave-like properties? And this is where we get this idea of particle-wave duality, where particles have a wave behavior, waves have particle behavior, and really both are a little bit of both. All matter has a little bit of wave to it, all wave has a little bit of matter to it. You could think of it as, or a little bit of particle to it, is a better way to say it. Let's see what this one does. I'm so glad these are all working now. They weren't working before. Okay, so here's our laser. And we're going to do 2 lasers and we're going to watch them interfere. Actually, let's just do this one. Turn on the laser. So laser, and it spreads out and it's got this, intensity on the wall and everything else. This is what it looks like when we treat light like a wave. When you treat light like a wave, it all comes out in this continuous stream, and it's all kind of together and all this stuff. So that is how we treat light usually. If we treat light like particles, like photons, this is more like we have to think of it as it comes out in these packets of light, right? It comes out in a packet of light. So there's a photon that comes out, there's another photon that comes out. Of course, it happens much more quickly than this. Put it on the rapid. So it's coming out in little packets of light. So fast we can't even see the different packets, but it does that, and that's fine. And if we have 2 lasers, or 2 light sources side by side and we turn them on, right? And we give them the same color-ish. So where is this one?
Just backed out both of them on their estimated
You can't see that color.
Oh, no, I meant the intensity.
But up here we can still see that there's a I'm going to put it up here in the green where we can see. And we'll see some interference with these. If we get about the same color light, we should get a better interference pattern. We start to see interference patterns. So here's our interference pattern. When we get light right between the two lights, right? It's like getting light right between two doors. We wouldn't expect that maybe, but that's what we expect with waves, and so we know that light's a wave. But what if we start to look at this in terms of electrons, right? So we have electrons coming out. If electrons are kind of like waves, that's what we see. If electrons are like single particles, then we see particles coming out and hitting the screen like this. So these are all the particles that hit the screen. And it's just continuing to fill with particles apparently. And if we do this one, let's see, can we do this one with particles? No. Okay. So here are the electrons hitting the screen all over the place here. And why can't I do particles over here? I want to do particles here.
I'm assuming it does
Oh, lost one. Oh, here we go. I can do it over here. So here I've got my, if I have my electrons coming out, and we'll do hits. So we're looking at hits. So those are the number of hits that we've got. That's great. And we're going too fast, so let's go down to low. Go down to low intensity, and let's reset it. Off. Reset. Now let's look at a double slit pattern. We're going to start with light. Actually, let's go, yes, so we'll start with light. And let's do this, and let's turn it on. On. Photons coming out. Let's see, so we get what we expect here. We see the photons build up in the bright spots, and they don't build up in the darker spots quite so much. Change frequency, reset. See, we get an interference pattern there. And it turns out with electrons, we actually get the same kind of thing. We send out electrons and we get hits, and we get also an interference pattern. It's maybe too bright to see it, but let's try it again. So we get an interference pattern right between the doors. We get a bright spot, and one's over here as well. It does happen. This is obviously not a real experiment, but if it was, that's what we would see. Not what we would not see what we would expect. Just two marks on the walls, one for each door, for electrons. And that's what started getting people to think that maybe we need to start thinking about what is it that is a wave about. What is it that is a wave about electrons? What is it about electrons that give them a wave? And it's not just electrons. Protons do this too, and other small particles. And the bigger particles you get, the less it does it, and then eventually the pattern is very difficult to see. But we suspect that it's just good for all matter. Well, we know that it's good for all matter now, according to our theories.
So if you did it with a machine gun in theory enough, eventually we'd see it.
It's not about doing it enough. It's about doing it in the right conditions so that you can discern the pattern. So for a machine gun, I think the thing that you'd have to do is have the smallest bullet possible and the highest speed possible. Is that right? No, maybe the lowest speed possible. I don't know. But anyway, this is what it comes down to. The scientist who is actually a graduate student, Louis Victor de Broglie, he did some thinking about this and came up with a proposal for what it is that makes matter a wave. He said that two things you can calculate the wavelength of two things using this new equation for the momentum. Remember, the momentum was equal to h over the wavelength. Well, if you rearrange it, you get wavelength equals h over momentum. And if you use the momentum for things with matter in this equation, you get one wavelength. And if you use the momentum for things without matter to them, like light, you get another wavelength, but you still get a wavelength. And so they said maybe this is how you calculate the wavelength of matter, is you take Planck's constant and divide by the momentum that matter has. So the smaller your momentum, in other words, the slower you're going, the bigger your wavelength. But it's still a very small wavelength. But what is it a wave of, is the question. Because all this equation gives us is a wavelength. It doesn't tell us what kind of wave it is. And later on they discovered that it's actually a wavelength of probability. What is a wavelength of probability? We were doing probabilities on this table the other day, right?
Yeah.
The wavelength of probability tells you, a wavelength of probability tells you for matter, different things about that matter. For example, the wavelength that is associated with a proton will tell you where that proton might be. Remember, we can't tell where a proton is. Remember, we had to do that indirect experiment where we fired things at it, but we can't actually see it. In truth, a proton you can't actually determine exactly where a proton is. You can only determine within a certain probability. And that probability length, the distance of the probability has a length to it. So we don't know where a proton is exactly, but we know it's within this certain length. That is the wavelength of the proton. And that length depends on the speed. The faster the proton is going, the harder it is to figure out how big it is, because it's harder to measure something that's going fast. So the wavelength gets bigger the faster it's going. Sorry. Is that right? Bigger, smaller.
The wavelength
If it's going faster, the momentum is bigger, so the wavelength is smaller. Sorry. The smaller it's going, so the harder it is to measure it. Right? It's harder to measure something small than it is to measure something big. There we go. So it gets confusing again. But anyway, the point is that these wavelengths are very small to begin with. And so if you want to measure it, you need to make it as big as possible. So you need the thing to be going small. So if you want to measure the wavelength of a particle, you have to make it go short, very slow, which means you have to slow it down in some way. And the wavelengths are not something that you can measure using a ruler anyway, because they're wavelengths of probability. The waves are actually probability waves, not waves. They're not like a length of a boat or something. And it's not a wave of electricity, so you can't measure it using a voltmeter. You know, it's different than light. It's not a wavelength like light is. So this is another mystery to add to our boatload of mysteries that we've created in this 2-semester course so far. But we can calculate the matter waves, we call these matter waves, of anything now. So I want to measure the matter wave of something macrocosmic, like your chair. The momentum of your chair is going to have to be determined and in some frame of reference. And then you're going to have to take Planck's constant, which is a really, really tiny number, and divide it by the wavelength, by the momentum of your chair, which may be some number, but it's not really going to be that big. So no matter what, the wavelength of you're going to have a super tiny wavelength for the wavelength of that chair, which means that chair is where it is.
we're pretty sure we know.
Yeah, we know where it is. It's right there, right? It's not going to end up in Carney or something, because its probability wavelength is smaller than the actual chair is, much smaller. But if we did have a wavelength for that chair that was 100 miles, then that chair could exist anywhere within, and in fact does exist everywhere within that wavelength. So this gives a whole new meaning to length contraction and length expansion. No, I'm not. In reality, what we discovered is that matter, especially on a subatomic level, does not exist as individual things, definable things, as a definable volume. Is that matter actually is variable until you actually measure it. And that's maybe a bad way to think of it, but it's probably the best way I can explain it. In other words, atoms, the size of an atom is only determined by the measurement being taken. So it's kind of funky. But everything at the quantum level is funky.
I'm glad we know
Yes.
that. At least it's.
So we're going to leave it at that. You guys can be done for today. I'll get some homework put up online for you.
Are you gonna do it like you did last time?
Yes, I am. I'll try to do a little bit better job though.